Hi, guys. So, I want to take you through this study guide about the basic calculation and interpretation around correlation. So, correlation, first of all, starts with taking an ordered pair, and we take the x value out of that ordered pair, and we find the z-score for that x value. And then we do the same thing with the corresponding y value in that ordered pair. We find its z-score. We take the product of those two values. So over all of the different ordered pairs in our data set, we add up all of those products, and then standard deviation involves n minus 1 degrees of freedom. So we do the same thing here. We multiply by 1 over n minus 1, and this is the formula for correlation. So you're not going to have to use the formula for correlation in order to do these kinds of calculations by hand. The most important thing that I want you to realize is that correlation is calculated by using z-scores, and that in particular explains a lot of the relationships inside of interpreting correlation. So R measures only the strength of a linear relationship between two quantitative variables. So if the relationship is not linear, correlation isn't a reasonable way in order to measure its strength. We'll see that in just a second. So next, correlation can't be any lower than -1, and the correlation's value can't be any higher than +1, and it has no units of measurement. So z-scores have no units of measurement, so that means that the calculation of R, the correlation, also has no units of measurement. So first, what I wanted you to see is let's calculate the correlation between the number of manatee deaths and the powerboat registrations in Florida. So in order to do that, a couple of things. Here's the scatter plot of that data set. So you should already have these data in list 1 and list 2. So let's go ahead and make sure you know how to set up the scatter plot. If I press second y equals, I want to go into plot number 1. I want to make sure that it's turned on. I want it set to the scatter plot option using powerboat registrations in list 1 and manatee deaths in list 2. So in order to get that scatter plot graphed, then you can simply press zoom 9. And that will give you the scatter plot that we are looking for. So the direction here is positive. So as the number of powerboat registrations increases, the number of manatee deaths increases also. So it looks like a relatively linear form. I can certainly see a linear trend there, and it's a relatively strong relationship, and we're going to be able to measure that by calculating correlation. So before we actually do the calculation for correlation on the calculator, it's important that you turn the diagnostics on. And in order to do that, please do the following on your graphing calculator. So if you have not done this already, press the second button and then press the number 0. This brings up a catalog of all of the possible commands. They are alphabetized on your calculator. Press the down arrow and scroll through this list of commands until you get to diagnostic on. Here is the command diagnostic on. Put the arrow next to the command diagnostic on, and then press enter twice. So here's how then we calculate the correlation. So press the stat button, go over to calculate, and you could use either of the linear regression commands. I'm just going to use the first one because it's most convenient, linear regression. So on my operating system, I'm going to run the linear regression command, and it will assume that I am using the data in list 1 and in list 2 unless I specify otherwise. If you have a menu that appears, just make sure your X list is list 1 and the Y list is list 2. You can highlight calculate and press enter. And the value that I'm really interested in right now is just here, the correlation, which is 0.953 if we round it to the nearest thousandth. So something to think about, that's a really, really high correlation given that it can't be any higher than 1. So the correlation between the number of powerboat registrations and the number of manatee deaths, we calculated that as 0.953. So this linear relationship really is strong because the value of r is so close to +1. So what I wanted you to realize, though, is sometimes we can have relationships that are strong, but because they aren't linear relationships, we don't get a very high correlation. So if you remember the data comparing speed and fuel consumed by this European Ford Escort, so that relationship was clearly not linear. So running the correlation, finding the correlation for those data, the truth is this really isn't a very good idea because correlation is used to measure only the strength of a linear relationship. So, and you don't have to do this on your own calculator, I just want to see what's happening here. So linear regression, if I select that command, what I want to do is run, if you will, the linear regression between speed and fuel consumed. So there's speed, and then I want to select fuel consumed. So notice you get a really small correlation, relatively close to 0. It's negative 0.17. So the correlation between speed and fuel is negative 0.17, but even though the relationship is very strong, it's not linear. So it exhibits a very weak correlation with a value of r that's close to 0 because correlation really only measures the strength of a linear relationship. So we shouldn't be surprised that between the speed and the fuel data, we get a relatively small correlation close to 0 because this isn't a linear relationship. It doesn't look linear at all. So R does not distinguish between explanatory and response variables. So the explanatory variables, those are the x values, if you will, and the response variables are the y values in the model. So a correlation that is greater than 0, that indicates a positive association. And shockingly, a correlation that's less than 0 suggests a negative association. So, and again, this shouldn't be much of a surprise if you're changing the units of measurement. If you change the units of measurement, that has no effect on R. So because understand the correlation is calculated using z-scores, so changing units of measure aren't going to change the values of the z-scores. But notice these are z-scores, and inside of these calculations, we're using the mean for x and y and the standard deviation for x and y. What this means is that correlation is not resistant. What we mean by that is it is not resistant to outliers. The mean and the standard deviation are certainly affected by outliers, so that means that correlation can be strongly affected by outliers. So let's look at the powerboat and manatee data in example 3 and example 4, and let's purposely create some outliers and see what that does to the correlation. So again, if I go back to my graphing calculator, here is the actual data. I'm going to press Stat and Enter, and I'm going to go to the very bottom of the list, and I'm going to put in a new observation here. So now, it's not a real observation. We're purposely making an outlier. So let's add an observation where there are 950,000 powerboat registrations. So I'll enter a 950, and we'll act like that's associated to 20 manatee deaths. So I'll put in the 950 and the 20 deaths. And if I zoom 9, I can see that outlier right here. So it certainly does not follow the overall linear trend in this model, in this data set. And I can see that it's reflected in the correlation. If I press stat and calculate, and again, run the linear regression command on L1 and L2, I can see the correlation has decreased. Just from that one observation that we put in there, the correlation is now 0.876. So we created an outlier in the scatter plot, and the correlation decreases to 0.876 when we do that, because that point is not consistent with the linear pattern. Let's go ahead and change that point then. Again, I'm going to act like we have an observation with 1.6 million powerboat registration. So we'll enter the 1600, and we'll say that's associated to 164 manatee deaths. So I'm going to press stat and enter, and I'm going to take out the 950 and the 20. I'm going to replace it with 1600 and 164. So I'll press zoom 9 in order to see my scatter plot, and clearly I can see that this point is an outlier in the sense that it is away from, its x and y values are both unusual within this data set, but it does continue to follow the linear trend within this data set. So this outlier actually strengthens the correlation, it increases the correlation. So we have an outlier. And in some sense, I suppose you can think about this in terms of a gap. We have a large gap between this outlier and the rest of our data set, and that's simply because the outlier has an unusual both x and y value for this data set. But notice the correlation, what happens to it if you actually take the time to calculate it. So I'll go to my linear regression command again and execute that on list 1. And list 2, now the correlation is increased to 0.970. It was around 0.95. It increases to 0.970. And the reason it increases is because this point is consistent with the linear pattern. So just a couple of more details to consider. It's very difficult to really guess the value of correlation just by looking at a scatter plot. So most people can't look at a scatter plot and say, oh, that looks like a correlation of about 0.41, or that looks like a correlation of about negative 0.75. That's really not a skill anybody has. It's very difficult to do that. So because correlation is calculated using z-scores, and z-scores are based on means and standard deviations, it's customary to report the mean and the standard deviation. Of both variables, of both the explanatory and response variables when correlation is calculated. That's something you might see in professional literature. So last up then, a correlation can't be any lower than -1, and a correlation can't be any higher than +1. Again, correlation is between -1 and +1, and having a correlation of exactly -1 or exactly +1, those indicate exact linear relationships between the variables. So a correlation of +1 would represent an exact relationship, positive relationship between an explanatory and a response variable. A correlation of -1 would represent an exact negative relationship between an explanatory and a response variable. And tomorrow we'll spend a little bit of time doing example 5, where we're going to look at an exact positive relationship and an exact negative relationship. And we'll actually do briefly the correlation calculation so that you can see that positive and -1 really are, if you will, the boundaries of how low or how high a correlation can be.